Howdy everyone, and welcome back for Chapter 8 example problems. Here we're going to focus mainly on Lewis structures and how we draw them, and then some things we can get from them. Chapter 9 will have more of that, of draw the Lewis structure first and then do stuff with it. But formal charges can be a little tricky for some people. Resonance can be tricky for people. So we want to look at a couple problems to see how that all works and go from there. Alright, so we're going to do the full thing for HCN, that's hydrogen cyanide or hydrocyanic acid, whichever way you're using it. We want to get the Lewis structure and formal charges for it. Now the one rule is whatever comes first goes in the middle unless it's hydrogen. Then you kind of move on to the next one. So we'll put a carbon in the middle. That's step one. Draw single bonds to the hydrogen and the nitrogen. Alright, so that's the end of step one. Step two is give the outer atoms an octet. So nitrogen has 2 electrons with that bond there, so it needs 6 more dots. So we go there. All right. Hydrogen only ever needs 2 electrons, so hydrogen will never get dots, so stop there. Step 3, we need to count. We're having how many we're supposed to have total electrons. That's from the periodic table. We compare it to how many drawn electrons we have, and that will tell us when we subtract them how many needed electrons we have, if any. All right, so the total electrons, hydrogen's in 1A, so that's 1. Carbon is under 4A, so that's 4 more, so we're at 5. Nitrogen is under 5A, so that's 5 more. We are supposed to have 10 electrons. When we look at what we've drawn, we have 2, 4, 6, 8, 10. We have 10 electrons drawn. When we subtract, none are needed. We're not missing anything. So step 4, add the missing electrons. Well, we skip over it. There aren't any. All right, but then we come to step 5. Does this central atom still need an octet? And the answer is yeah. The carbon has 4 electrons from the 2 bonds. It needs 8, and there's no more to add. So that's when we say, okay, well, if we can't add any more dots, now we need to move those dots, move the electrons by making double, possibly triple bonds until we get there. So we're going to say, okay, let's take these 2 electrons and make a double bond. And so we'll have an N and then the H there. And we say, okay, 2, 4, 6. The carbon atom's still not there, needs 2 more. So we'll take those 2, move them, because there's nothing over here to move, make a triple bond. And then if we look at that, yep, the hydrogen has the 2 electrons it wants. Now the carbon has 2, 4, 6, 8. The nitrogen still has 2, 4, 6, 8. Everything is fulfilled with the octet rule. There's still only the 10 electrons we're allowed to have. That is our final Lewis structure. So we're good there. Now for formal charges. Remember that formal charges are equal to the valence electrons that are coming from the periodic table minus the bonds and the the non-bonding electrons. So for the hydrogen is under 1A, so that's 1. When we subtract, it has 1 bond and no dots. So 1 minus 1, it has a formal charge of 0. That's good. For the carbon, that's under column 4A, so it should have 4 electrons to start with. The carbon makes 1, 2, 3, 4 bonds. It also has no dots. So 4 minus 4, okay, formal charge of 0. And for the nitrogen, it's under column 5A. It has 3 bonds, but it also has 2 non-bonding electrons. 5 minus 5 equals 0. And that's what we want to see. Formal charges are typically best if they all equal 0, or at least that's the goal if there's any alternate ways to draw things. And so for many normal compounds, you get a formal charge of 0 for many things if you're doing what you're supposed to. So that works out well. So now we have a Lewis structure, we have our formal charges, we're good to go here. All right, for the second example, we're going to make it a little bit different. We're still going to do Lewis structure and formal charges. We're also going to add in oxidation numbers because there is a problem in your homework set that asks you for these, and you might be thinking, how do I do that with Lewis structures? There is a way, but the problem in particular, you can also solve using the same rules we used back in Chapter 4, which is why I'm going to do this example. We can also use the same rules for oxidation numbers we used in Chapter 4, and it will work out, so that's why I'm doing it this way. All right, so for this one, we have the phosphite ion, PO3 minus 3. So phosphorus in the middle. We'll have our 3 oxygens surrounding it. There's step 1. Step 2, give the oxygens an octet. I'm just noticing that this drawing tablet I'm using is making all my oxygens into like octagons. It's really weird. All right, so there they all have an octet. Now when we get to step 3, our total, how many electrons we're supposed to have? Well, each oxygen brings 6 because they're under 6A, so 6, 12, 18. Phosphorus is under column 5A, so that's another 5, so 18 and 5 is 23. But here we have to look out for our minus 3 charge. That means we've added 3 extra electrons to get this negative 3 charge. So 23 plus 3, we are supposed to have 26 electrons. Now for the drawn electrons, we have 8, 16, 24. We've drawn 24 electrons. When we subtract that, we have 2 electrons that are still needed. So now we come to step 4. If there's any extra electrons that still have to be drawn, put them on the central atom in pairs. So we'll put them here on the phosphorus as a pair. Then we check step 5. Does the central atom still need an octet? We have 2, 4, 6, 8. Nope, it's already got 8. We stop there. And then the final thing, because this is an ion, we're going to put the whole thing in brackets and put the negative 3 there so that any reader look at this says, is that just PO3? No, it's PO3 with a negative 3 charge. It's the ion. All right, so that's done. Now for oxidation numbers. Put that over here. Kind of separate that off. We're still going to use the same rules we used in Chapter 4. Those rules were that a neutral element is going to be 0. Well, we're doing molecules and ions, so no, nothing's going to be 0 here normally. There might be a case where in a really complicated molecule something's 0, but not here. We're saying, okay, hydrogen is normally +1. Fluorine or fluoride is almost always -1. Or no, is always -1. And then oxygen is usually -2. And so, hey, we have our oxygens. We are just going to assume that oxygen is -2. Just assume that. The other rule we had was in a molecule, in a polyatomic ion, if you add up all the oxidation numbers, they must add up to the charge. That means that the phosphorus plus the 3 oxygens, that's an oxygen, not 30, must add up to equal -3. Well, we just said oxygen's -2, so that means phosphorus minus 6 must equal -3. Okay, that means phosphorus must be +3. So that's how we get oxidation numbers using the same rules as Chapter 4. Just say, okay, if I see a hydrogen, assume something. If I see oxygen, assume. If you see fluorine, assume. And then figure out the rest from there. If the problem has you solve for one element first, and you're like, but that's not the way maybe just, if you see that you're solving for oxidation numbers, just solve for all of them on paper first. Then you can type them into the computer, whichever order they want them in. All right, last thing, the formal charges. All right, so here, formal charge, we'll start with the phosphorus. Phosphorus is going to be, well, it's supposed to have 5 electrons from column 5A. It has 3 bonds, so that's good. It's got 2 dots. That means this phosphorus has a formal charge of 0. That's good. For the oxygens, they are under column 6A, so they're supposed to start with 6. They're all equivalent. We're going to pick one of them. So this one on the bottom, say it has 1 bond, and it has 6 dots. So that's 6 minus 7. That equals -1, and that's okay. Oxygen's the more electronegative atom, so it should be the more. It should have the negative charge if there is one. But then we say, okay, the rule, just like oxidation numbers, are that formal charges must add up to the overall charge. Well, we have 3 of these oxygens, so if we have 3 things that are all -1, they add up to -3, that checks out. So in this case, we have 2 different ways of kind of saying what are the charges. You get different numbers, and in some molecules, the oxidation numbers are kind of more accurate. In some molecules, the formal charges are more accurate. In most cases, it's somewhere in between. But that's not here or there. It's just, well, what's the problem asking for this time? All right, so there's an example of everything for Lewis structures. Hoping this helps. The other stuff in the problem set are often found just by using Coulomb's law about sizes of atoms, going back to the chapter 7 stuff, or the electron configurations, just saying, okay, remove the last electron that were added, or add electrons to the end. You guys can do that. All right, so hope this helps. Have a good one, and I will see you in chapter 9.